And I'm actually going to turn to a further set of introductions and introduce our first pair of speakers for this session, which we are calling Industrial Livestock Production, Fish Farming, and Global Climate Change. And first, we're going to hear from Dr. Samuel Myers. Dr. Myers is a senior research scientist at the Harvard T.H. Chan School of Public Health and the director of the Planetary Health Alliance. His current work spans several areas of planetary health, including the global nutritional impacts of anthropogenic CO2 emissions, the health impacts of burning in Southeast Asia, the nutritional impacts of reduced access to wildlife, especially bushmeat in the diet in Madagascar, the local in the Madagascar context, and global consequences of fisheries decline for human nutrition and health, and the impact of animal pollinator declines on human nutrition at a global scale. So that's quite a lot. And in addition to that, as director of the Planetary Health Alliance, Dr. Myers oversees a multi-institutional effort to support research, education, and policy efforts around the world, focused on understanding and quantifying the human health impacts of global environmental change and translating that understanding into resource management decisions globally. So with that, I'm going to invite Dr. Myers to give his presentation before we turn it over to Mike McCloskey. And then at the end of that, I'll invite both of our speakers to respond to each other for a few minutes, and then we'll open it up to some questions from the audience. Thank you. So Sam, do you want to share your screen and kick us off?
Yes, thank you. I do. Let me see if I can make this work. All right. Well, gosh, it's such an enormous treat to get to be here with all of you. And I'm having this slightly startled, disoriented experience already, having just listened to that presentation and feeling like I'm watching these different communities that I actually didn't know anything about. I'd never heard of the Feral Atlas, from a huge variety of disciplines sort of feeling their way towards the same set of issues and the same reality. And so I want to present to you a framework that we're calling planetary health that's really an expression of many of the exact same questions and concerns about the Anthropocene that's coming out of the global health community, in hopes that it will underline some of the things that you're already thinking about, and relates a lot to some of the opening comments that Jim Scott made as well. I think that, planetary health comes out of this really unique moment in human history that's already been spoken to. And in many ways, there's never been a better time to be a human being, right? So over the last sort of 75 years, we've seen these really extraordinary improvements in most metrics of human development. And, literacy has nearly doubled among adult population globally between 1940 and 2015. The percentage of the global population living in extreme poverty has dropped from 62% to about 10% in only 65 years, despite a nearly tripling of that population. Life expectancy has risen dramatically. Child mortality has fallen by a factor of 4 during that same period. And so we've seen these really extraordinary improvements in these metrics of human development, but the same extraordinary developments in science and technology that have fueled these improvements in education and wealth and health in really just one person's lifetime have also been driving this extraordinary ballooning of humanity's total ecological footprint. And both Anna and Jim mentioned the Great Acceleration. And the extent to which this is an extraordinarily new phenomenon. So if you look at these metrics of global human consumption over time, whether you're looking at appropriation of fresh water or proliferation of motor vehicles or production and use of synthetic fertilizers, paper production, plastic production, primary energy use, they all look very similar with these relatively modest consumption patterns up until about 1950. And then this very steep, almost exponential growth in our patterns of global consumption. And not surprisingly, if you look at metrics of the state of natural systems over that same period of time, you see similar patterns, whether you're talking about global biodiversity loss or exploitation of fisheries or addition of carbon dioxide to the atmosphere, ocean acidification, chopping down of tropical and also temperate forests. And the reason that all of these graphs look so similar was already sort of previewed by Jim, that they're all underlain by these two sort of more fundamental trends in global human population growth. And the population's grown by somewhere around 2.5 billion only in 1950 to well over 7 billion today. And this even steeper acceleration in per capita GDP growth. And when you multiply those things together, you see this really kind of astonishing growth in total world GDP, this nearly vertical line that we're sitting atop of. And so it's hard to overstate how recent this massive ballooning in the scale of the human enterprise really is. And, every year now, in order to feed ourselves, we've converted about 40% of the total terrestrial land surface for croplands and pasture. We're using about half the accessible fresh water on the planet, mostly to irrigate our crops. We're exploiting 90% of monitored fisheries at or well beyond maximum sustainable yields. We've cut down between 7 and 11 million square kilometers of the world's tropical and temperate forests. We've dammed over 60% of the world's rivers, and that number is on its way up to 92% in the next couple of decades. We're dealing with this growing problem of air, water, and soil pollution globally. You all know we're disrupting the global climate. And as a result of all of these sort of large-scale changes, we're losing species about 1,000 times the baseline rate. In addition, the population sizes, the number of individuals within populations of mammals, fishes, birds, reptiles, amphibians, has actually fallen by around 65% since 1970. So that's that replacement of wild fauna with domesticated fauna that Jim was talking about. And the latest IP-BEST report last year, the global assessment, suggested that there are about 1 million species now facing extinction, many within decades. So the impact of this global ballooning of our ecological footprint has been quite extraordinary. The core premise of the field of planetary health is that the scale of the human enterprise now exceeds our planet's capacity to absorb the wastes that we're producing or produce the resources that we're using sustainably. And as a result, our activities are transforming most of our planet's natural systems. And so I think it's very similar to this framework of the Feral Atlas, although nowhere near as elegant. But that as a result, we're seeing not only global climatic disruption, but pollution of air, water, and soil. We're fueling the 6th mass extinction of life on Earth. We're altering biogeochemical cycles like the nitrogen, phosphorus, carbon cycle, huge changes in land use and land cover and scarcity of resources like fresh water and arable land. And that all of those large-scale anthropogenic environmental changes are interacting with each other in complex ways that we're just starting to understand, which affect the core proximate conditions for human health and well-being: the quality of air we breathe, the quality and quantity of food we can produce, our exposure to infectious diseases, our access to fresh water, even the habitability of some of the places that we live. And the result is that we're seeing significant impacts across every dimension of human health. And so for the purposes of this conference, we're going to focus on nutrition and food systems, but we equally could have just as interdisciplinary and broad a community sitting down to talk about infectious disease exposures, non-communicable disease exposures, mental health outcomes, conflict and displacement. So there's no dimension of human health that isn't being significantly affected by this vast transformation of nature. So we'll focus a little bit on nutrition. And before thinking about how nutrition is changing, let's just take a quick snapshot of where we are with nutrition. And the answer is we're not doing so well right now. So we have about 820 million people who go to bed hungry every night. There are about 2 billion people suffering from micronutrient deficiencies. And undernutrition is associated with a big share of global child mortality. At the same time, that we're dealing with this metabolic disease pandemic. And so the results of increasing obesity, more sedentary lifestyles, and these shifts in diets have led to a lot of metabolic disease, things like high blood pressure and heart disease and diabetes. So we're not doing so great at the minute, right now. And when we think about the future, I guess the way I frame this is around this idea of sort of a triple challenge. So as we look into the future, we're going to need to really achieve historic increases in our production of nutritious food to feed this growing population. We're going to need to do that despite encountering these very extensive environmental headwinds, which are actually constraining our ability to produce nutritious diets. And somehow we need to do both of those things while actually reducing the ecological footprint of our global food production system if we're not going to completely destroy the biosphere in the process. And so this is a graph from a book that we just published a month ago that's sort of the first big textbook of the field of planetary health, but where we're looking at global food production over time. And the point here is simply that, you know, if you look at the period of the Green Revolution, you see these extraordinary period of growth in per capita food production that we've never seen before. And we're going to have to maintain that historic rise in food production in order to keep up with demand. At the same time, we've got to lower these environmental impacts. So the main driver of this sixth mass extinction of life on Earth is our food production system as a result of habitat fragmentation and loss of forage. Food production system obviously is also a huge contributor to pollution of air, water, and soil, global changes in land use and land cover, driving water scarcity and aquatic impacts, and is contributing around a quarter to a third of greenhouse gas emissions and driving climate change. And then there's this third part, right, which is how are we going to do this in the context that human health is nested in a set of ecological conditions, and nutrition is particularly nested in those conditions because the food production system is based on a set of biophysical conditions upon which it rests and which are now changing at the fastest rates in the history of our species. So changes in temperature, changes in precipitation patterns, more extreme weather events, degradation and loss of arable land, changes in air quality, actually ground level ozone reduces crop yields, water scarcity, biodiversity loss, the pollinator declines that Anna was just talking about in Colombia, all impact our capacity to produce both the quality and quantity of food that we need. And I thought I'd just give you a few very quick snapshots from this is just another way of thinking about the same thing, but a few snapshots from our research to show you some of what I'm talking about. So I've been involved over the last 3 years, or actually now more like 5 or 6 years, on 3 major research projects. One has been looking at how rising concentrations of carbon dioxide in the atmosphere are actually making our food less nutritious, and working with a group of agronomists all over the world, we measured 41 different cultivars of 6 staple food crops, things like rice and wheat, sorghum, maize, grown on 7 locations on 3 continents over 10 years. And we built a big sample size of these grain samples grown under these face conditions. You see this ring in the bottom left corner. And these are CO2 emitting jets. And in the center of the ring will be a CO2 sensor and a wind direction sensor. And when the CO2 falls below a prescribed level, the upwind jets will release some more CO2. And so you can maintain the CO2 inside the ring at a prescribed concentration. In our experiments, it was 550 parts per million, which is where the world will be probably the middle of this century, unfortunately. And then you can look at the cultivars grown inside the ring and identical cultivars grown outside the ring, which experience the same soil, the same weather, the same pests and pathogens, but they grow at different CO2 levels. And what we found in a paper that we published in Nature in 2014 was that there are actually significant reductions in critical nutrients like iron and zinc and protein in these staple food crops when you grow them at these elevated carbon dioxide conditions. And we've spent the last several years modeling what that means for the populations of 152 countries around the world and for their risk of deficiencies of these nutrients, which are a big deal from the public health standpoint. What we found was that between 150 and 200 million people are likely to get pushed into new risk of deficiencies like iron and zinc deficiency, in addition to the billion or so people who already have those deficiencies and for whom they will be exacerbated. So that's a significant, global health challenge. Another area where we're doing a lot of work actually right now is in these pollinator declines that Anna was talking about. In fact, we just finished an analysis that we haven't even finished writing up, but that where we're calculating the global health burden of having not enough pollinators today. And by stitching together data from the pollinator ecologists and from agronomists and from global food trade experts, we're actually modeling the yield reductions from inadequate pollinators, and then how those foods would have moved through the global food trade system, which populations would have been able to access them, and what consumption of those pollinator dependent foods would do for human health. And we're finding close to 500,000 deaths a year that we're experiencing today from inadequate pollination services, and also huge economic costs. And then fisheries degradation is another area where particularly ocean warming is leading to these major changes in the distribution, the sort of geographic distribution and the size of fisheries around the world, with the dominant trend being that fisheries are moving away from the tropics and toward the poles. And we've been modeling the vulnerability of the human population to losing access to wild harvested fish in the diet. We found that about 1 billion people are getting important, like around 20% contributions of critical nutrients like omega-3 fatty acids and vitamin B12 and iron and zinc from wild harvested fish, and are living close to a threshold of sufficiency. And so we define that as our vulnerable population, who, if they lose access to these wild harvested fish, are at risk for significant health impact. So this is just to give you a little feel for the kind of work that we're doing around understanding how these rapidly changing environmental conditions come back to affect our own health and well-being, which is the focus of planetary health. And so, these are a few of the areas within the question of nutrition and planetary health where we're working. As Sarah mentioned, we're also working on on wildlife declines in Madagascar and their effects on nutritional outcomes. And then, of course, there are a million other ways that environmental conditions are changing which affect food production, including these surprises. Like, you can't essentially radically change all the biophysical conditions that underpin the food production system without experiencing some surprises along the way, like the fact that our food's getting less nutritious in response to rising CO2. Of course, we could show a very similar kind of diagram for every other dimension of health. So we're talking about nutrition here, but we could do something similar across the other major dimensions of health. And then when we think about, so sort of where do we go from here, and we focus a lot on this in our book, there's an enormous amount that can be done, right? There's an enormous amount to address these problems that I'm talking about, and they really fall into these 3 domains. So the first domain is clearly to reduce food waste. And given that globally we're losing around 30 to 40% of the food that's being produced, both in poorer nations as well as in the global north for different reasons. And the ecological footprint of that food waste is absolutely enormous when you think about all the environmental inputs that go into producing that food that's never used. So there's a huge opportunity around reducing food waste, which a lot of innovative work is going into right now. The second area is changing what we eat. And so just as Jim emphasized at the beginning around domesticated animals, and I certainly don't need to tell this group about dietary change, but there would be obviously huge benefits in terms of reducing the ecological footprints of our diet if we were consuming less meat and more plant-based diets. There also would be enormous health co-benefits, which is kind of a recurring theme in planetary health, is often the things that we need to do from an ecological standpoint are also good for us from a health or sometimes economic standpoint. And then The third area is sort of these new production approaches. And this is, I think, a very, very interesting and exciting time in global food production because there's so much happening. Everything from sort of rediscovering old principles from agroecology to new sort of technological innovation around precision agriculture, AI, robotics, to whole new processes like protein fermentation, the production of synthetic milks and eggs and meats, to even, we actually are just finishing a paper right now about entomophagy, about the role that domesticating insects and consuming 5 grams of insects a day could actually dramatically reduce micronutrient deficiencies across sub-Saharan Africa and South Asia. So there's a lot that can be done. We can talk more about it, obviously, as we go on in the conference. I did want to mention to you that there is an organization that I direct called the Planetary Health Alliance. There are over 200 organizations in over 45 countries now that are part of this alliance. That I think it's I really want to learn more about the Feral Atlas and more about your community because I feel like we're feeling our way towards similar things. But we would definitely welcome your participation. It'd be interesting to talk about how to be engaged together, particularly around our annual meeting, which is coming up in April and will be virtual. And then, as I mentioned, we've just written this book about planetary health. So I want to let you know that that's out there and exists and uses a lot of the same kinds of ideas that I've already heard. So I'll stop there. Thank you very much.
Sam, thank you so much. You've certainly given us so much to chew on. And I hope that everyone will continue to, don't mean to make a pun this early in the day, but ruminate on some of those ideas as we move towards Mike McCloskey's presentation. So I'm going to introduce our next speaker. Dr. Mike McCloskey was once described as the Steve Jobs of the dairy world. And his experience ranges from his multinational veterinary training that started literally at the back of a cow, to his recognition as an industry leader in dairy, capped by creating a nationally recognized brand that has recharged fluid dairy sales. He's committed to pushing farmers, politicians, NGOs, and anyone who will listen down a path to a more sustainable future for the dairy industry. He's the founder of the cooperative Select Milk Producers and also of the nation's largest agritourism attraction, Fair Oaks Farms, which is one of the largest dairy farms in the country and milks over 16,000 cows, including an 800-cow robotic dairy farm and an 800-cow organic dairy farm. And he's a pioneer of the process flow for using cow manure to create renewable biogas that power tractor trailers that haul milk to market, and the process of using filtration to fractionate milk and harness the desired attributes of dairy. So Mike, I'm going to turn it over to you and invite you to share your screen and share your presentation with us.
Thank you, Sarah. It's a real pleasure to be here today. And I'd like to just start out with a few comments to kind of set before I jump into my slides. So, milk has a growing worldwide recognition for its high nutrient value because of this, milk has a global annual growth rate today of over 3%. So also I'd like to share that here in the US, milk production has a great history of being sustainable. So let me give you some examples of this. And let me take the last 70 years. The last 70 years, we've been able to decrease our land use by over 80%. We've been able to decrease our water use by over 80%. And we've decreased the national dairy herd size by 75%. And while doing this, we were able to more than double our milk production. This resulted in about a drop of 2/3 of our greenhouse gas emissions. Today, the dairy industry represents less than 2% of the total greenhouse gas emissions of the United States. But it doesn't stop there. Just recently in April, dairy farmers in the entire value chain of dairy joined in and made a commitment to do a combined goal of reaching net zero no later than 2050. Now, this will not be an easy task. It will take policy shifts. It will take state and federal government support and incentives. It will take the private sector to join in with us. It will take great research from really our grand land universities that have done such a great job over the years in our research that are poorly funded today. We need those universities to find that funding, and we need to help them find that funding. But I have a strong belief, and I hope that through my presentation, I can share some of my visions and thoughts, that agriculture will be one of the solutions to global warming. And not only global warming, but other environmental problems that we have, such as eutrophication that's been mentioned here today, and biodiversity, and many others. So other emissions that we have, such as ammonia emissions. And as I run through my presentation today, I hope that you can share that vision with me. So with that said, I'm going to jump into my slides. So what I'm going to do for about 1 minute is take you through the fastest tour of a dairy farm ever done. And let's start with the farming. So we farm a great amount of forage. Corn silage on the upper left side of the screen there, and alfalfa on the right side of the screen. And it's not only about the quality of forages that we grow and harvesting at the right time, but on the bottom of the screen, it's about how do we preserve them so that we don't have any waste and we can deliver that high nutrition to our dairy cows. And then on the left side of the screen, you can see one of our dairy farms. The green roof is a milking parlor. The long barn, the parallel to each other, is where the cows live. And this is kind of the environment that we have created for our cows. So it's an environment that protects them from the elements. We deliver this excellent feed, have feed in front of them on an ongoing basis. We take care of them from heat stress in the summers. We take curtains to protect them from the cold weather in the winters. It's our responsibility of dairy farmers to make sure that these animals are safe, that they are never mistreated, never abused, and that they always find comfort in what they do. So we have these nice sand beddings where these cows can lay down. They love to lay down 12 hours a day, and they chew their cuds and take naps. They get up every 2 hours to eat again. They need to have feed in front of them all day long. Then we also have the milking parlor portion of the dairy, where safety is first. It's about the safety of the product that we're harvesting, milk. It's about the safety of our employees, the safety of our cows, and the care that we have for all of these. And then it's about the young stock that we grow in the farms that will replace our dairy cows. So a lot of genetics, and we're going to talk about that, and raising young babies. To the bottom right side of the screen that shows these yearlings that are about a year away from becoming dairy cows, and to the top right of your screen of having their first baby and joining on milking herds. And the last part of the dairy is manure management, which then completes the cycle of going back to the farm. So these photographs are approximately 20 plus years old. And back then it was a very acceptable system, and some people are still practicing this today. But it was something that we knew we needed to advance. So in the last 20 years, this is kind of the evolution that we've been through. And it's been a lot of work to be able to figure out how to lead and change in this area. But believe me, in these screens, there's millions of dollars invested of research on the farm of how to do things better. And today, this is what our manure management looks like. So we are just doing some amazing things that I want to share with you here when we get into the details of greenhouse gas. But with that, I'm going to take you to the breakdown of where the greenhouse gas emissions are coming from. So basically in a farm, we know that we have an enteric emission, which is basically the belching of the cows. Some rectal gas, which is less than 10% of that. This is all about methane. The manure, which when in the pits and in the lagoons, will go into an anaerobic fermentation and produce methane that's going to atmosphere. And I think everyone knows that methane has about 30 times more the density of CO2, so it's a very serious greenhouse gas. And then there's an area of feeding and farming that produces greenhouse gases as well. And this is not about methane, it's more about nitrous oxide, which is even 10 times more potent than methane as far as its ability to retain heat in our atmosphere. And also it's about fossil fuel fertilizers, and it's about fuel that we use to run our tractors through the farm. So that's what adds up that 2.8. And then on the energy side of the farm, which is kind of the smallest one of all, that's obviously about fossil fuel electricity and fossil fuels to run our tractors, for a total of 10.6 pounds of CO2 equivalent per gallon of milk produced. So it is our goal as dairy farmers of how are we going to take this to a zero emission by 2025. So first of all, let me start then with the enteric emission. Remember, this is all about methane release, and this is the belching of the cows, and it represents 35% of our total greenhouse gas emissions in the dairy industry today. And we have it's, as we saw before, 3.69 pounds. So one of the things that we are focused on is ration optimization. So just to give you a quick idea, there's cows out there producing 7 and 8 gallons of milk. There's cows out there producing 12 gallons of milk. And the genetics throughout our US herd, which is 9 million cows, is extremely similar, all spread out through the US. So this is the lack of production per unit is not a genetic restriction. It is more on from the moment that we grow our feed, how we process that feed, how we care for it, and then how do we balance these rations in the proper manner to maximize productivity. So you could imagine between the spread I just gave you, there's over a 25% difference. So maximizing that 25% is extremely important. Got a little problem here. Okay. And then number 2 here is continuous improvement of feed digestibility. Yes, here there's a little bit of seed selection. There's a lot about hybrids, and there's GMOs, improvement in digestibility, and gene editing, and other ways that we continue to improve the digestibility of our feeds. So therefore, the productivity and the carbon imprint of producing those feeds is better utilized in productivity. That's the idea here. And then between 1 and 2, you know, when we combine that and put it into our model, looking at 2050, we're seeing over a 20% decrease in methane. And that's a very, very conservative approach because we're only using the previous trends of the last 20 years to calculate those. And we know that there's going to be a lot more improvements in both 1 and 2. The third one, genetic selection, and I'll just put up the 4 different major categories that we're dealing with in genetic selection, is very impressive. So we have an abundance of growth in milk production over the last 70 years, as I shared with you, and that's been in a great part to our excellent genetics. But in the last 10 years, since we have really understood the genomics of the dairy cow, this is really accelerating. And then with the advent of in vitro fertilization, we have really been able to accelerate the quality and the selection for milk production. So just to give you an idea, with that time period of the 70 years, we grew approximately at 1% per year in our genetic improvement. And now the calculations are that we're growing at 3%. So you can imagine what that impact's going to have on productivity per unit once again. And feed efficiency, there's cows, same weight, producing the same amount of milk. One may be eating 60 pounds of dry matter, one may be eating 50 pounds of dry matter. That is a heritable trait that we have identified, And we can now, over our selection of genetics over a period of 5 or 6 years, we can decrease by 10% the amount of feed that a cow would need with the same production. So this is very exciting and something that we're already starting to use on a practical way through the first genetic company that I'm working with, called Sexing Technologies. As a matter of fact, we'll be at the farm within 2 weeks to present this to a group of local dairy farmers. We also, in health and wellness, through genomics, we're able to do some great stuff. And this last one, I think this is just enormous. The spread here in sheep is amazing. You know, there's sheep that are producing 80% less methane than others, and that's a genetic trait. And in cattle, we believe we're using a range of 20 to 30%, but we're just starting to understand this well and starting to identify, and work is starting to figure out on genomics, how can we start selecting for this? So I think this will have one of the biggest impacts, and it's one that's just starting. So, and then I'll use this last one as feed additives. There's one, I'm gonna just use one as an example. 3-NOP is the name of the product. It's not commercially available in the United States. It is in Europe and other countries. It's being processed at the FDA right now. We're going through a lot of studies because they want to consider it a drug instead of a feed additive, but nonetheless, we'll get there in the next 2 years is our hope. But this is produced by DSM, a company from the Netherlands, and it will, its research shows decreases of 40% of methane. And it changes the metabolic pathway into butyric acid, which allows us to have more productivity out of that same energy. I believe that this is just a great discovery. We have many other feed additives. I'm sure you've all heard about a bunch out there that are being worked on. And it's an area that has great promise, but we already know that a product like this, and we just used in this model, 30% decrease in methane production. So how do we pay for this? Carbon credit incentives will come along to help us as we invest in all of this. Hopefully, as carbon values increase for decreasing carbon, that these incentives will help be able to get this to be adapted nationwide. We are calculating a reduction of 70% through all of the above, and that is a conservative approach for 2050. I think we'll reach that way before then and be able to even get that lower. So we're very excited about this. One thing I want to point out here is that these practices, any dairy farmer can do it. It doesn't matter if you have 50 cows or 1,000 cows. There's not a single practice on here that is scale related. So that's an important issue because we can take this concept and this knowledge around the world. The next area that we talked about is manure. So 3.54 pounds, 33% of the total farm gate. And I'm going to take you through a series of pictures. The first one is this one, which is a digester. In the background, you see a concrete up on the hill there that has over 2 million gallons of manure in it. It's retained in there for about 18 days. We produce a biogas. We collect that biogas. And that was a methane that was in those pits that you saw in one of the photographs. It was going to atmosphere. It does not go. We collect 100% of it. We put the manure in there before it starts fermenting. We clean the alleys where the cows live 3 times a day as they go into the milk barn and bring it directly to the digester. We collect all of this gas and we do several things with it. One is, this is a genset that produces 1 megawatt of electricity, but also, as you can see in the left-hand side of the picture, we collect all the heat off there as well. So we have an efficiency of over 88% on this engine. And we use that heat to warm the incoming manure in the digester, which needs to be at 100 degrees. We also clean the biogas to 99% natural gas, so a renewable natural gas, and we run vehicles with that. And then after the product comes out of the digester, we are just finishing up a technology that we've been working on for the last 4 years. And it came from investments that Mr. Gates did with Genicky Engineering to be able to create this, what they call this omni processor, which is made for the some villages in poor areas of the world where they could go into these septic holes and take out the waste and process it and create a fertilizer and potable water. And that's what's occurring in this picture. And when I saw this 3.5 years ago, I reached out to Peter Janicki, who's in the photograph there, and we formed a partnership called Cedron Agriculture to be able to create this equipment. And so this is a Varcor, as we call it, but it's so this does 90 gallons a minute of manure from our dairy cows, and the previous one does about 1 gallon a minute. So, but we were able, Mr. Gates allowed us to use all that technology to develop this. So it was just very, very grateful of him. And this is just an amazing piece of equipment. And what it does is it ends up with 3 products. So after the digester, and we've collected all the energy, we go straight into the Varcor. We end up with a dry fertilizer to your left, which will then from here go to a pelletized product that then we can knife into the ground so that we can no-till. In the middle, you have a product that is 20% ammonia. So it's aqueous ammonia at 20%. It's organic product. And it rivals anhydrous and other fertilizers of nitrogen that are made out of natural gas. And to your right, you have clear water. That is water that's ditch ready or potable water that is the only third thing that comes out of here. So between the digester and the Varcor, we've been able to eliminate all the pits and ponds you saw. Now we're in the process of doing this. This is our second one only. It's new technology, but over the next 5 years, we expect all of our dairies to be operating this way. And you end up with a dry solid, aqueous ammonia, and clean water. So if you go back to the digester concept, you have the manure coming from the cows and from the barn straight into the anaerobic digester, producing energy, eliminating greenhouse gases from those pits, but also offsetting fossil fuel because we're producing renewable fuels, and therefore you do not need to use fossil fuels for that same product. From the digester, we go into the Varcor and produce the products I mentioned before. I want to make a point here to remember these anaerobic digesters are full of manure. They're very stable. They're at a great pH and full of just billions of bacteria starving, wanting more food, because at the end of the presentation, I'll show you what we're doing with that as well. So going back to the greenhouse gas reduction. So this was all about methane, 100% about methane. And as I said, we do renewable through gas and electricity that you saw in the pictures. We create applicable fertilizers, and we are able to get some ecosystem credit incentives that we're working on, which are based on carbon, nutrient trading, which I don't have time to get into this, but it's very, very positive for eutrophication and other issues. And RINs, which are a environmental credit given by EPA. Not going to spend a lot of time explaining this right now, but it's a really good environmental credit and very positive. And then the low carbon fuel standards, which is started in California, and this is a great environmental credit that pays us for a really good return so that we can afford to invest in these types of technologies. And then finally, these E-RINs, this is real important because these E-RINs sit at EPA and they're not being used, but we're working with EPA to be able to start using them. They've been there in the Renewable Fuel Standards Act of 2014. And this concept will allow us to put digesters on dairies that are as small as 500 or 400 cows. That would be over 90% of the milk in this nation. And I'm very excited about this program. We're very focused on it. So as you can see again on this slide, there's a lot of stuff for all dairy farmers, not just scale, but it does take scale to start these type of technologies. Like in any technology, as you get them going, you drive down capital costs, you drive down operating costs, and you drive up efficiency. And therefore now we make them more available for all dairy farmers in that process. And here we expect we have a total reduction of 93% of that 3.54 pounds. The other big area is feed production. As we said, 2.8, 27% of the total farm. You know, this is not about methane. This is about nitrous oxide, as I shared, about 65 to 70% of these 2.8 pounds come from nitrous oxide, which is 300 times CO2. And also it comes from fossil fuel fertilizers, which, as you saw, we are able to eliminate with the process of the fertilizers I shared with you. And then about 5% is fossil fuels, which, as I showed to you, we are working on engines that now can run 18-wheelers and tractors, and I'll show you that in a second. So basically, renewable-based fertilizers that will take us to no-till. No-till is a big game changer here, something that I've always wanted to do all my life as a dairy farmer and wasn't able to do because we had to till in our manure as we applied it to our fields. Now, in the state that we've converted these renewable-based fertilizers, I can inject them into the fields and I don't have to till, and by no-tilling, you reduce the nitrous oxide release, or reduce the substantially the nitrous oxide. We use cover crops, so this is important in this process. Crop rotation, as you saw, the different forages that we use, and we have a lot of small grains that we use in silage and haylage. Now, under this scenario, you can apply the 4 R's, so the right stuff, the right amount, in the right place at the right time. This is something that we have to get so much better. It's precision agriculture. We as farmers have to focus on this. And the technology that I just shared with you allows us to do such a better job of this. Better water use in a no-till crop. There are a lot better water use. You have substantially reduced erosion, reduced fertilizer, herbicide, and pesticide application. The set aside and filter strips is something that goes very well in this combination. So I'm not going to spend a lot of time on that, but this is a big push for us. This starts creating, as you look above this last bullet point, it starts creating some biodiversity back into our farming and microorganisms, vegetation, and wildlife. But the bigger play here is sequestration. So once we're able to go into this no-till, we're able not to disturb the ground. We allow the carbon forage on top of the ground. We allow the root structures to stay down deep inside the ground. We are seeing a great amount of carbon sequestration through this process. So, and we used a model here that's fairly conservative. There's, I believe, over the next 20 or 30 years, this sequestration and our ability to do things with our crops is going to be very impressive. So again, here we need carbon credit incentives. So we need these policy shifts that I talked about. We need nutrient trading incentives that we don't have. We'll need policy shifts to trade there for a total reduction of about 130%. Again, most farmers can get involved in this. There's going to be some time period for us to take technology such as the one that produces the dry fertilizer and stuff, to be able to get them down to a scale, but we're headed in that direction.
Excuse me, Mike. I'm sorry to interrupt, but we do need to move soon to discussion. So if you could.
So let me jump to the end real quick. So I'm going to jump all that and just leave you with. Sorry about that. So here's a 10.6. There is what the baseline based on the numbers we're going. So we're looking at a negative 3.39. I am very comfortable with this last aspirational. As a matter of fact, I believe we'll beat that as well. But here is a 4.7 pounds of carbon sequestered as you apply all those technologies. Thank you, and sorry for going over.
Thank you so much, Mike. No, and sorry to cut you off. We just want to make sure that there's so much rich material on the table. We just want to make sure that we leave some time both for you and Sam to respond to each other and to take some questions from our audience. So as Elizabeth Wood mentioned, please do private chat any questions for our speakers that you do have. In the meantime, I'm going to invite both Dr. McCloskey and Dr. Myers to respond to each other's work just for about 2 or 3 minutes each. And I don't know if either of you would like to start, if you've got something on the tip of your tongue. There's lots of really interesting overlaps and dialogues between both of your presentations. So if either of you would like to jump in, or I can call on someone.
Well, I'll jump in if you don't mind, Sam.
Please.
So, you know, I enjoyed Sam, your presentation very much. You know, it is so inclusive of everything that's going on out there, and I can only present from my daily life what I do every day. My goal is to be able to improve what I have my hands on. I truly have enjoyed Anna and Sam's presentation because it is the way I live. It's the way I think. But I have to think within the world that I go to work every day and produce in every day. So what we do is we look at everything. How do we do things better? But I am 100% aligned with the concerns and the presentation and both of the previous. And it's what gets me going every day. It's what makes me think of what is the next technology I need to work on and develop so that I can try to do my small part as a farmer in that. So I just wanted to lay out that I really enjoyed both presentations tremendously.
Thanks, Mike. Yeah, no, it's wonderful to go from all this slightly abstract and conceptual stuff to seeing pictures of cows in the field. So thank you for grounding the conversation. I find myself, when I'm listening, holding attention between two very different sort of thoughts or questions. One is this enormous admiration for the sort of systematic approach that you've described and the commitment to figuring out how a whole industry can go through its entire sort of life cycle chain and find these efficiencies and make these really significant improvements. The question that's running through my head, and it's not a field I know very much about, so it's not a loaded question at all, but is this question about the trend towards protein fermentation and synthetic production of everything from meat to milk to eggs, and this really interesting trend of using microbes to produce the proteins that, you know, are the basis for these products. So whether you're talking about Impossible Burger or these new synthetic milk companies. And so I'm curious, on the one hand, the work that you're describing seems extraordinary and incredibly effective. On the other hand, the proposition of using a large mammal to produce a mix of proteins and fats and sugars for us to consume seems like a sort of odd proposition when you think about it from a purely sort of technological, you know, position, and you think about the capacity of microbes to do all of that more efficiently with a dramatically smaller footprint. And so how do you think about this trend around protein fermentation and the production of these synthetic proteins, and how do you think that's going to affect the dairy industry going forward?
It's a great question. So, you know, obviously I struggle with that as I see different technologies evolve. Let me share a few thoughts because I approach it from probably 2 or 3 different angles. The first one is that, you know, milk is more than just protein. So, you know, you got a fermentation vat making casein and some whey protein, but milk has 9 essential ingredients. Protein is a very important one within milk, but so are many of the other 9 essentials. Obviously it has, now today we recognize there's some high quality fats within milk. Research is very clear on that. But then it has, known to us, 32 micronutrients that are extremely valuable to what they do from a metabolic and nutrient point of view. So to, you know, it's something that I don't think that easily we will get a comparison. Now I believe that in certain ingredients, that we have, such as certain powders that are used in baking or somewhere else, you will find that's the entrance to some of these fermentation milks, for example. But as a nutritional package, it's going to be a while. I'm not saying it won't happen, but milk is something that has evolved over 200 million years of mammals being around, and it's been the natural selection. It's what every infant drinks for the first year of its life. It grows every single cell in its body and creates this incredibly healthy toddler. And they have received nothing else. And it's all the nutrients combined in milk that allow us to do that. So you talk about your deficiencies of iron and others that you mentioned very clearly that I agree with. I could tell you that the line of deficiencies that would occur by not using the natural product of milk could be enormous. So it's not a substitute in my mind, and it won't be for quite a while. The other thing is our impact in rural America. I believe it's very positive. Our employment, what we do, the vibrancy of the towns that we live in. We talk about agrarian lifestyle, so it's something that's very important. Once you go to a vat in a city and you're producing something like that, that impact is, but that doesn't give us a right at all. What it does is it says, you know, these are good businesses to have. So therefore I have to approach it and say, well, what are the negatives of milk? One of the big negatives is environment, and this is why my effort is on this environment. So if the industry, if we as a society can turn around farming from the impression that it may have in the public's eyes today to the impression that I have in my eyes, that we actually are a solution to where we can say, no, we're not emitting 10 pounds, we're sequestering 6 pounds for every gallon that I deliver to you. Plus I'm delivering you this great nutrition. So I have to live in that world because I don't have a choice. I have to think that way, but I really believe that way. And I really believe that we've seen many cycles in my lifetimes about, you know, no fat and eat more sugar or low fat. And, you know, we caused a lot of problems. I think there's a lot of nutritional stuff that come back to bite us. I expect to see that in the new evolution of all the foods that you mentioned. In the meantime, I'm very focused on making sure that milk stays prominent, that we have high quality, value added products from milk that are very nutritious. But at the same time, when we go back to the farm, we have taken incredible care of our cattle, that they are cared for in a spectacular way, and that our environment is cared for and improved from where it was today. So that's the approach I have to have.
Great, thank you both.